Hello everyone, this is Professor Roman. Welcome to the first lecture in my course, Transition to Advanced Mathematics. This is the class I teach at the University of California, Irvine. The purpose of this course and this book is to prepare you for the study of advanced mathematics, specifically upper division university level mathematics. And this is actually a three-part process. The first part involves the study of the rudiments of mathematical logic. And this will provide you with some training into how to think logically, which is a skill that's absolutely critical to the ability to learn advanced mathematics. The second part of the process is a careful look at proof techniques, and that is essentially an application of logical reasoning to topics in mathematics. Finally, there are several topics in mathematics that are essential to the study of more advanced math, and yet don't seem to have any place in a traditional math class. So this is the perfect place to go over those topics. One of the things that a transition course should do is to begin to alter your perception of mathematics, if necessary. The issue is that courses such as elementary calculus, linear algebra, differential equations that are generally taught in the first 2 years of undergraduate study are not representative of mathematics in general, because they tend to be recipe-driven. In other words, the main goal of these elementary classes is to teach you how to solve problems by following a script. So the emphasis is placed on how you solve a problem and just how in general, rather than the why of things. And there's very little discussion of the underlying theory behind the topics that you're studying. And students, in my experience, tend to expect that. Many students will say, don't tell me why, just tell me how. How do I solve this problem? And that attitude has to change to be successful in upper division math courses. Emphasis switches to an understanding, a study of the underlying theory, and also to the construction of proofs. To justify mathematical statements, proofs are critically important to justify a mathematical statement. We can't rely on our intuition to simply say this is true because it sounds true to me. There are too many times when that reasoning fails, and we'll talk about that later on in the lectures. So this book and this course provides the preparation necessary to meet the challenges of upper division math courses. Not just the mathematics itself, but the approach, the attitude you have to take to be successful in doing upper division mathematics. Prerequisites for this course are very minimal. Frankly, the most important prerequisite is a strong interest or an abiding curiosity in mathematics. Of course, any lower division math classes that you've taken will be helpful because they'll provide some experience, but they're not, strictly speaking, necessary. You don't need to know calculus or linear algebra or differential equations to understand this course. There are a couple of references here and there to elementary calculus and mention of matrices once in a while, but if you're not familiar with those topics, it's not really going to affect your success in this course. On the other hand, while talking about prerequisites, it is going to be difficult to discuss mathematics without the need to mention functions from time to time. They're so fundamental to most of mathematics. And we will devote an entire chapter in the book, in lectures in the series, to a detailed look at functions with formal definitions and so on. But before reaching that chapter, which is some way down the road, I'm still going to want to use the concept of a function very simply from time to time in examples and so on. And so I've included in the appendix to this book a very brief look at functions. This is what it looks like. It starts here, a brief look at functions. It's this page and half of another page. So it's a page and a half. It's material you may already know, but I strongly urge you to look it over, read it, make sure your terminology matches my terminology. It'll just, that'll pay off in the long run. I did the exercise sets a little differently in this book than I have in my past books. For the most part, I sprinkled exercises throughout the text. And that is in the hope that it will encourage you to attempt the exercises in real time, so to speak. As soon as you encounter an exercise, you should attempt to work it. There is a notable exception. The chapter on proof techniques, I put all the exercises at the end of the chapter because part of learning how to do proofs is in deciding which technique might be applicable. And I don't want to give you that information ahead of time. It's not a service to you to do that. So if under this material on direct proofs I gave immediate exercises, and then under proof by contradiction I gave another set of exercises, you'd probably guess which technique is applicable in those cases. So I left all the exercises for the end, so you have to make that decision. I didn't do it to be nasty. I did it because it's something you need to cope with. It's part of the process. There are solutions to virtually every exercise at the end of each chapter. I don't think it's universal, but pretty close to. So you have all the information you need to work exercises and check your solutions for accuracy. Okay, so that's basically the preface. One more thing. I included the Greek alphabet here for your reference. I will use Greek letters. All mathematicians use, to my knowledge, use Greek letters in their writings. The Roman alphabet is just simply not big enough, the 26 letters. I did my best to include as many letters as I could, but I only came up with 26, and it's not enough. And that's a joke. You know, my last name is Roman, so anyway. The Greek alphabet is very handy because it adds several more letters. Not all the Greek letters are used often, some of them very seldom. I very seldom see Omicron being used. Upsilon is another one I hardly ever see. But most of them do pop up from time to time. And so you should, as you study advanced mathematics, you should become comfortable with the Greek alphabet to the point where you don't need to use this table. But it's here for reference in case you need it. Let's take a brief look at the table of contents so you can see basically how the course is organized topic-wise. First chapter, entitled Introduction. Here is where I give you an overview of mathematics in general with an eye towards the foundations of mathematics and how mathematics evolved in the late 19th century into a formal discipline. Mathematics is an ancient discipline dating back, say, to the year 3000 BC, possibly farther back. But it didn't really take its current shape until the late 1800s. So we'll talk a little bit about that. I also want to show you some unsolved problems in mathematics that seem like they should be solved by now but are not, and that's sort of a curious thing. I'm hoping it'll stimulate your curiosity about mathematics. There's a lot of things that you probably aren't aware of, and we'll talk about that. That's the first chapter. The second chapter is the first of two chapters on logic. Propositional calculus is the simpler form of logic. We will be able to study what are called arguments, logical arguments, and identify when they're valid and when they're not, which is very important. But the propositional calculus, unfortunately, is not powerful enough to be sufficient to do mathematics. So we also have to study something referred to as the predicate calculus. Incidentally, the word calculus here doesn't have anything to do with integral and differential calculus. A calculus is just a logical system of reasoning. So the predicate calculus will add to the propositional calculus. It will enhance it to give us things that we need, specifically things that are called quantifiers, so that we can incorporate phrases that we use all the time in mathematics into logic, such as for all sets, so and so happens, or for all functions, such and so happens, or there exists a function for which such and so happens. So we can't, those phrases, those mathematical statements don't make sense in the propositional calculus, but they do in the predicate calculus. So we'll go over all that in detail at the time. Chapter 4 is on proof techniques. This is obviously critically important, as we discussed. It's one of the three main goals of this course. The next chapter is where we begin studying some of the topics that I mentioned we have to study because they don't fit into other classes, but you need them for advanced mathematics. We're going to take a look at sets and multisets. Multisets are not mentioned very often, and it's a simple concept, and it's way underutilized. So we'll talk about that. It just takes a brief discussion, but it's a very, very handy concept. And so we'll talk about families of sets, set operations, union, intersection, so on, disjointness, power sets. Much of this you probably already know, but I'm sure there are some things here you are not familiar with. Next chapter is on mathematical induction, which is a proof technique. And it's a proof technique that's very powerful but very specialized. So when it works, it tends to work really well, but it doesn't work as often as we'd like, let's say. Next chapter is entitled Combinatorics, the Art of Counting. Counting is an important topic in mathematics. And it doesn't mean just 1, 2, 3, 4, 5. We like to be able to count a lot of different things in mathematics. And so we'll talk about that. Combinatorics is a branch of mathematics all by itself. There are mathematicians who specialize in it. They're called combinatorialists. Then we turn to the subject of binary relations on a set. Relations are very common, not only in mathematics, but throughout life. Next chapter, partitions and equivalence relations. Equivalence relations are a key concept in upper division mathematics, advanced mathematics. But what I've noticed is that oftentimes in the first stages of upper division mathematics, equivalence relations aren't used explicitly or mentioned explicitly nearly as often as they should be. And I think part of the reason for that is that there is a tendency or hesitancy on the part of professors and writers of textbooks to think that students already understand this concept, so we can just go ahead and use it. And so it's a shame. There's a couple of topics like that. Partially ordered sets is another one, where if I met a junior level math major, I would not be at all confident that that person understood equivalence relations or partially ordered sets. I would have to ask, have you studied equivalence relations? Have you studied partially ordered sets? And it wouldn't surprise me if the answer was no. So we are covering this material. This is where it belongs. It is standard material for a transition course, and it will put you one up on students in your upper division math classes who have not studied these concepts. Then there's a chapter on functions I mentioned earlier. We'll go into careful detail about how functions work and talk about things that you may not have heard about in calculus courses: restrictions and extensions of functions, formal definitions of surjectivity, injectivity, and bijectivity, and so on. The final chapter is on cardinality, and this is a fascinating topic. As it turns out, that when we talk about the sizes of sets, for finite sets there's very little controversy, you might say. Everybody knows what it means to say a set has 3 elements or 10 elements. And a set with 3 elements is smaller than a set with 10 elements. But for infinite sets, things are different. It turns out that there are infinitely many different sizes of infinite sets, just as there are infinitely many different sizes of finite sets. So some infinite sets are larger than others. And that surprises people who don't study mathematics sometimes. They would think, well, either a set is finite and I can count the number of elements, or it's infinite and that's the end of the story. It's not that simple. And so we will go into some detail on this idea that infinite sets can vary in size. So that's a look at the table of contents of this course. Okay, let's take a look now at Chapter 1, which is an introduction to the course and what is mathematics. Mathematics is many things. It's a science. That is to say, it's a systematically organized body of knowledge. Mathematics is the cornerstone of all physical sciences and technology. Without mathematics, we wouldn't have physical sciences, we wouldn't have technology. Mathematics also plays a very significant role in the biological sciences and even the social sciences. Mathematics is also an art form. I looked up the term art in Webster's dictionary, and the definition is something that is created with imagination and skill, and that is beautiful, or that expresses important ideas or feelings. I can't think of anything that could fit this description more accurately than mathematics. Mathematics is also, arguably, the most difficult academic discipline that we know. Even if you don't agree with that, there is, I think, certainly no academic discipline that requires more dedication than mathematics. Mathematics also teaches us several very important skills. It teaches us mental discipline. It teaches us how to think or reason logically. It teaches us how to think with precision. It teaches us how to construct precise logical arguments. In mathematics, these arguments are called proofs and are used to establish mathematical facts, which are often called theorems. I'll talk about these terminology of proofs and theorems and so on a bit later. But one thing to emphasize is that mathematics is essentially all about proofs. Proofs are everywhere. On occasion, when I teach an upper division math class, one or two students will complain, oh, he did proofs all the time, too many proofs. Well, that's what mathematics is about. And hopefully you will be convinced of that as we continue our discussion. Let me give you an example of the kind of thing that mathematicians find interesting. Like specialists in every academic discipline, mathematicians have a specialized set of interests. So do physicists, so do chemists, so do artists, so does everyone. But unlike most other disciplines, many of the things that mathematicians find interesting are of completely no interest to the average person. That's a shame, but that's what it is. Here's an example of the kind of problem that mathematicians find interesting to varying degrees. As you probably know, a positive integer is prime if it has no positive factors other than 1 and itself, which must always be factors. In 1742, the Prussian mathematician Christian Goldbach wrote a letter to Leonhard Euler, who was one of the greatest mathematicians of all time, in which he asked essentially, in slightly different terms, the following question. Is every even integer greater than 2 the sum of two prime numbers? The conjecture that this is the case is called the goldbach conjecture. The goldbach conjecture is one of the oldest unsolved problems in mathematics. And there is a prize of $1 million that will go to the first person to either prove the goldbach conjecture or find a counterexample. The prize, by the way, is offered by the Clay Mathematics Institute at the Collège de France in Paris, and it should, of course, be split with the professor that first introduced the solver to the conjecture. Just keep that in mind. Certainly, the goldbach conjecture is very simple to state, but it alludes to the fact that some very simple sounding problems seem to lie beyond our ability to solve at the present time. Many very brilliant people have thought about this conjecture, especially considering the $1 million prize, yet no one has been able to find a solution one way or the other. If we check some small integers, there'll be no surprises. 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5. Everything on the right here is prime. 10 is 3 plus 7, it's also 5 plus 5, and so on. In fact, very powerful computers have checked all the even integers up to 400 trillion. and found that the Goldbach conjecture holds at least up to that point. So that would seem to support Goldbach's conjecture, but be very clear, this is by no means a proof. For all we know, the integer 400 trillion and 2 is not the sum of two primes. We don't know. So all we get from this is a sense that maybe it's true. The fact is that in the last more than 275 years since 1742, no one has been able to settle this question. Now, most mathematicians think that problems such as this are actually quite interesting. They are bothered, as I am, by the fact that this simple-sounding problem seems beyond our present ability to solve. One would like to think that problems that are simple to state should have simple solutions. That is far from the truth. Now, I wouldn't want to suggest to you that every mathematician has spent time thinking about the Goldbach conjecture. That's certainly not true. Mathematics is a huge field of study, and mathematicians will specialize in only one or a handful of areas, relatively small proportion of the total of mathematics. And those areas could be very far removed from the Goldbach conjecture. In fact, the Goldbach conjecture belongs to a branch of mathematics known as number theory, and that constitutes only a very small portion of mathematics. But even young mathematicians who specialize in number theory might be well advised to avoid spending much time thinking about the Goldbach conjecture. A young PhD may say, oh boy, I can make my fame and fortune if all I have to do is solve the Goldbach conjecture. Well, all I have to do is kind of misleading. And what you want to avoid as a young mathematician is spending several months, year, 2 years, 3 years, whatever, of your early career and end up at the end with nothing much to show. And the odds are against solving the Goldbach conjecture. So that can be very hard on a person's career. Broadly speaking, there are two types of mathematics and therefore two types of mathematicians, pure and applied. Now, these two types of mathematicians have far more in common than they have different. They both subscribe to the theory that the why of things is at least as important as the how. The difference is that applied mathematicians study areas of mathematics that have more direct applications to other disciplines, such as physics, chemistry, biology, computer science, or also other areas of mathematics. But it's important to point out that many areas of mathematics which seemed not to have much in the way of applications, which seemed highly abstract, have subsequently found applications. So what constitutes pure math and what constitutes applied math is a moving target. A striking example of this is the case of the mathematical discipline known as order and lattice theory, which we will take a brief look at in this course. This subject was introduced to the world in a formal way around the year 1900 by the famous mathematician Richard Dedekind, and we'll have more to say about him later. Unfortunately, it immediately drew intense and undeserved criticism from some prominent members of the mathematical community. For example, the famous mathematician Leopold Kronecker, in one of his letters, accused Dedekind of losing his mind in abstraction or something to that effect. And actually, Kronecker was not too good at judging what might be useful and what might not be, even though he was a first-rate mathematician. He was also philosophically opposed to Cantor's theory of infinite sets that we're going to go into quite a lot, infinite numbers. Kronecker so was at least 2 for 2 in his mistaken belief that certain subjects were too abstract to be important. That's a dangerous philosophy. I still see it today, but it is a dangerous philosophy. How, in fact, could the theory of order be too abstract? I mean, the order is all around us. Some people are taller than others. Some people are heavier than others. Some things are bigger than that. Order is everywhere, and it's everywhere in mathematics as well. So even though there still exists resistance to this idea that order and lattice theory is mainstream mathematics, and I have in fact felt that personally. I wrote a book on order and lattice theory. Today, those with a more open mind are finding applications for order and lattice theory. They're recognizing that this subject occurs throughout mathematics and that it has applications in such areas as quantum mechanics, for instance, computer science, even the modeling of terrorist cells in an effort to determine their weaknesses and how best to destroy them. Now, I'm not saying that it's a central feature in that discipline, but it does enter into it to some extent. Mathematics takes dedication. It's considered by many people, both mathematicians and non-mathematicians, to be the most difficult academic discipline, as I mentioned before. So it should only stand to reason that to successfully study mathematics, even at the undergraduate level, is going to require some serious commitment, some definite study time. And I like to draw analogies to this. I do this in all my classes, except for the very elementary ones. I don't know how well it's received, but it seems quite reasonable to me. If you wanted to learn how to play the classical piano, for instance, you're going to need to practice probably many hours a day. If you want to be a professional athlete, you're going to need to train many hours every day. To become a skilled brain surgeon, you're going to need to study very hard for many years. Well, at least the rest of us hope so. So why should learning mathematics require any less of a commitment than learning to play the classical piano or to be a professional tennis player or a brain surgeon? It just makes sense. Also, just like those other disciplines I just mentioned, mathematics requires participation. You've got to get your hands wet. You've got to plunge in and do things for yourself. You can't solve a problem, stay with it. Don't give up. Put it away for a day and come back to it another day. I do that all the time. The worst thing you can do is ask somebody else for the solution or look up the solution on the internet. It may relieve your temporary level of stress, but you're not gaining much from it. You're gaining a lot more if you can struggle with it and find the solution yourself. I know that's not always possible. Even I don't do that all the time. But it's something to keep in mind. The more you struggle with things, the more you think, the easier it will become. You can't learn to play the classical piano by watching someone else play, unfortunately. You can't become a professional athlete by watching sports on TV. You can't become a brain surgeon by watching Dr. Kildare, which you may not know was a TV series a while ago about a doctor. You can't improve your health by watching someone else jog. So it is with mathematics. You've got to get involved. You've got to do it yourself. Mathematics cannot exist without first establishing a sound logical framework in which to make sound logical deductions, valid deductions. Just as an example, here is an argument. If today is Tuesday, we will go to the bank. Today is Tuesday, therefore we will go to the bank. That is a valid, it is logically sound, it's logically valid, this argument. But this argument, if today is Tuesday, we will go to the bank, today is not Tuesday, therefore we will not go to the bank, is invalid. This is not logically sound. The conclusion, we will not go to the bank, does not follow from the two hypotheses. If you see that yourself right away, that's excellent. If you have to think about it for a while to see it, that's fine too. You would be surprised how many people believe this is valid. You've got to learn to, if you want to study mathematics, to distinguish between valid arguments and invalid arguments. And we will spend some time discussing all of this. It's part of the two chapters on logic. But now let's speak briefly about some of the developments that led to the formulation of modern abstract mathematics, the type of mathematics we study today. Even though mathematics, at least the written form of mathematics, would appear to date from the Sumerian period of around 3000 BCE, it wasn't until the 1800s, CE in the Common Era, that modern mathematics began to take shape as a formal and abstract discipline. In fact, while some very impressive and important mathematics was developed in the first half of the 19th century, in the early 1800s, such as, for example, the introduction in 1817 of the epsilon delta definition of continuity that is much beloved by all calculus students. And there was a very impressive work of mathematicians such as Évariste Galois, Niels, Abel, and others in the early part of the 1800s. It was not really until the late 1800s that attention was drawn to developing a foundation for mathematics, a foundation that was rigorous, stable, and contradiction-free. So let's take a look at how things developed, in particular in the area of modern set theory. The first thing that you realize when trying to set mathematics on a firm, logical foundation, so you're starting with a blank slate, is that you have to begin somewhere. You have to begin with some sort of object, some sort of mathematical object that gets the whole thing started. You can't do mathematics in a vacuum. You've got to start somewhere. The objects that form the foundational basis for mathematics are called sets. And the branch of mathematics that's devoted to the study of sets is called set theory. The subject of set theory was founded in 1874 in a single paper written by Georg Ferdinand Ludwig Philipp Cantor. We'll just call him Cantor. Cantor expanded and developed set theory in a series of 6 seminal papers that spanned a period roughly from 1874 to 1897. It's the very end of the 19th century. Cantor was strongly influenced by Richard Dedekind, who we spoke about earlier. He was the mathematician who developed the subject of order and lattice theory. And we're going to say quite a bit about Cantor's work much later in the course. It's fascinating. Cantor's definition of a set is the following. A set is a gathering together into a whole of definite, distinct objects of our perception or of our thought, which are called elements of the set. Well, I guess you can see that's not very precise. What is gathering together? What is whole? What are distinct objects of our thought? These things are a bit vague. The intention here is quite clear, but it's not very precise as a definition. But that should come really as no surprise, because if sets are the primordial objects, there's nothing before them. How can you even define? How can you even create a precise definition of set? You've got nothing to work with. You've got no other ideas to use to make a definition. We don't know what Cantor was thinking when he proposed this definition. I would assume that he had a feeling that maybe this isn't as precise as he would like it to have been, but I'm certainly in no position to second-guess Cantor. Maybe he was just trying to appease people who thought that the idea of a set was too abstract or too primitive to be useful. In any case, Cantor's definition is quite valuable because it does provide us with a starting point for developing an intuitive feeling about sets. Along with this primitive notion of a set goes the equally primitive notion of an element or member of a set. So these primitive notions, set and element of set, are by their very nature undefinable. We have to use our intuition. We have to hope it's accurate. There is no way to define the term set. You could say, well, a set of numbers is a collection of numbers. Well, then what's a collection? A collection of numbers is a family of numbers. Well, what's a family? It just doesn't work. Okay. The accepted notation, by the way, to denote the fact that little s is an element of a set, big S is to write this. And you've probably seen that notation before. And if S is not a member, little s is not a member of capital S, then we write this. But now, since sets are initially the only things that exist, the elements of a set have to be sets themselves. Everything is a set in mathematics, or something called a class, which we'll talk about a little bit later. But essentially, everything is a set. Sets are all that exist in the beginning, and everything is defined in terms of sets. So an ordered pair is a set, a matrix is a set, a function is a set, a real number is a set, an integer is a set. They're all sets. Of course, a mathematician doesn't generally refer to a function as a set, although sometimes, or a natural number as a set, unless there's a good reason to do so. It's certainly better to use a specific name for something than a generic name like set, when such is available, of course. Here's the definition of a subset, because we're going to need this, so I'll give it to you now. A set A is a subset of a set B, denoted this way, if every element of A is also an element of B. The set A is a proper subset of B if A is a subset of B but not equal to B. And then I use this notation. These two notations are quite common for subset and proper subset, but they're not the only ones. Of course, a set is a subset of itself, but it's not a proper subset. It's the only non-proper subset. The empty set, which you may know about, is the set that contains no elements. That is also a subset of every set. In the years prior to 1901, it was thought that every collection, gathering together into a whole, as Cantor would say, of objects that one can describe using symbols or words constituted a set. But in 1901, the mathematician and philosopher Bertrand Russell found a simple and easily explained inconsistency in the idea that every describable collection makes a set. Actually, Cantor himself admitted in a letter to Dedekind in 1899 that there were some inconsistencies in his theory, but it was Russell who pointed out this very simple inconsistency, which has now become known as Russell's paradox. Although, actually, Russell's paradox seems to have been discovered in 1899 by Ernst Zermelo, who we'll mention again, but he didn't publish his findings. That's kind of a bummer for him. Specifically, Russell pointed out that this collection, let me read it to you, I called it C. It's the collection of all sets S with the property that S is not a member of itself. Remember, the members of sets are sets. So you can ask, is this set a member of that set? And you can even ask, is a set a member of itself? This collection consists of the sets that are not members of themselves. It may seem counterintuitive right now to say that a set could be a member of itself, but remember what we are doing. We are starting from scratch. We are starting with this primordial concept of set, an element of set, that are undefined. We have to rely on our intuition. So we want to rely on our intuition as little as possible. So while you may feel intuitively that no set could be an element of itself, that is really something that's open to question. It needs further discussion, further comment. So this collection, then, is, again, the collection of all sets that are not elements of themselves. Now, if we assume that C is a set, it then becomes a candidate for membership in any other set. including itself. So now all we need to do is ask ourselves the question, is the set C a member of itself? The membership requirement for a set to belong to C is that the set is not a member of itself. So if C is a member of itself, it doesn't pass the membership requirement, and so it can't be a member of itself. In other words, if C is in C, then C is not in C. Well, that's absurd. On the other hand, if C is not in C, not in itself, then C does pass the membership requirement and therefore must be a member of itself. So we have an equally absurd statement. C not in C implies C is in C. But we're out of choices. We're out of possibilities. Either C is a member of C or it's not a member of C. In either case, we are led to an absurdity. And that is the paradox. Something is wrong. It's nothing wrong with the reasoning. So the only place we can turn to is the fact that not everything you can set down in symbols or words constitutes a set. There's another way to describe Russell's paradox that works if you're trying to explain it to someone who is totally devoid of any mathematics. It goes like this. Philip he lives in a small town. He's a barber. And Philip has the following rule, which is posted on a sign in the window of his shop. I shave all persons, and only those persons who do not shave themselves. Well, what about Philip? If Philip shaves himself, then according to his rule, he can't shave himself. But if he doesn't shave himself, then again, according to his rule, he must shave himself. So this is the lay version of Russell's paradox. So what do we do then? Well, we are forced to conclude that not everything we can describe in words or symbols will constitute a set. But that's a serious problem. We'd like to be able to discuss, within the context of mathematics, describable collections such as the one we made, such as C, the collection of Russell's paradox. One way to get out of this dilemma of Russell's paradox and have our cake and eat it too, so to speak, is to introduce the idea of a class. Classes are similar to sets. There are two types of classes, in fact. Sets are classes, but there are classes that are not sets, and they are referred to as proper classes. Many of the properties of classes are the same as sets. For example, you can take the union of two classes and the intersection of two classes. But the key difference is that a proper class cannot be a member of another class. Proper classes are not members of anything. And that is our loophole, because now when we look at this this collection that comes from Russell's paradox, we can say this is not a set, it's a proper class. And therefore, the question, does C belong to itself, goes away, because proper classes can never be members of other classes, of any class. Okay, so that's the notion of a class, which we will perhaps mention a couple of times. The most important use of classes for us will be the class of all sets. If you put all sets into a collection that is too big to be a set. We have the same issues we have with Russell's paradox, but the collection of all sets is a proper class, and so we can deal with it in that context.